Example 15.2 part B again asks us to write the given equation as a product of linear factors. Here we have x cubed minus 2x plus 4. The degree of this polynomial is going to be 3. And by the linear factorization theorem, I can write g of x as a times x minus c1 times x minus c2 times x minus c3. So that means we need to figure out c1, c2, c3, and we can actually figure out a right now, since we've seen that a is just the leading coefficient, and leading coefficient is already that implied 1. So I'm going to start with saying let a be equal to 1, but then we still need to figure out c1, c2, and c3. So let me come over here to this this equation, x cubed minus 2x plus 4, and when I first look at this, I notice that there are 3 terms, which lead me to think, ooh, maybe trinomial factoring. But the problem here is that you can only do trinomial factoring if the degree on that middle term is half of the degree of the leading term. And that's not what's going to happen here. So trinomial factoring is going to end up being a bust. So let me erase that. No good there. But maybe I need to think of it with a placeholder. Since it is degree 3 after all, this could be written as x cubed plus 0x squared minus 2x plus 4. And if I write it like that with a placeholder, then we might consider doing some kind of factoring by grouping. But that's not going to get you very far either. So what I'm showcasing here is the thought process that you would need to go through to try to get the factoring done for your equation. And when you have exhausted all of the reasonable possibilities, then your only choice is to go to the factor theorem. You can't not factor to be able to find the zeros. You just have to do that. So then the factor theorem becomes the only way for us to make this happen. So with the factor theorem, we're going to be looking at taking g of x and dividing it by an x minus c. Now, I'm not really wanting to sit here and just guess what I think c needs to be in order for the factor theorem to work. So instead, we use the rational zero theorem to be able to make the P over Q list. Your P over Q list is going to be given as plus or minus 1, plus or minus 2, and plus or minus 4. If you need more practice with that, you can always look at the previous sections 13 and 14. We saw, really more in 14, we saw the rational zero theorem there. And we need to now pick one of these to submit for C and see if it's going to work for the factor theorem. So I have to perform the division g of x divided by x minus c. I choose to use the synthetic division. I find it to be the quickest way to get to the point where I can find out what my remainder is. Set up my coefficients. You absolutely have to have the placeholder of 0 when you're doing synthetic division, otherwise it will not work. I'm going to go ahead and select -2 as the value that we're going to test. Now certainly you wouldn't know immediately which one of these 6 options, 1, 2, 4, or -1, -2, -4 is going to work. Now in the interest of the video length, I want to get on with the process. So I'm going to go ahead and select a value that I know is going to work. So if it's going to work, then that means we should end up with 0 as our remainder. And sure enough, we do. So with that remainder of 0, we have a theorem called the Remainder Theorem that would then say g of -2 is equal to 0. And anytime I get a statement like this, where I have a function value that is 0, that means that I have found a 0. That's the definition for finding a 0. So the factoring can now be started. I can take g of x, and I can now write it as the divisor times the quotient from the division that we just completed. The only time you can ever rewrite g of x like this is if you get a remainder of 0. So our divisor that we used in synthetic division was -2, but if we use that -2 to represent c, then that means the divisor for this process was really x plus 2, and then our quotient comes from the 1, -2, +2 coefficients, and that's to be interpreted as 1x squared minus 2x plus the constant of 2. So that initiates the factoring process that trinomial factoring and factoring by grouping just would not do. So now I would like to check to see, could I maybe attempt some trinomial factoring on the quotient? And you can try all you want, but you're not going to get any nice integers to make that work. So let's go on to the 0 calculation. Let g of x be equal to 0. So then I would get 0 equals x plus 2, or even 0 equals x squared minus 2x plus 2. And the first equation is going to give me some information that I already knew, and that is x equals -2 is one of my zeros. I knew that because synthetic division told me that. But 0 equaling x squared minus 2x plus 2, that's going to be the perfect situation for quadratic formula. And if you feel comfortable, completing the square would also work. I'm going to go ahead and use quadratic formula. X equals negative of b plus or minus the square root of b squared minus 4 times a times c, and that's all divided by 2 times a. So we'd want to simplify best that we can. Start with the negative, or the opposite of -2, so that'll be +2 plus or minus the square root of -4, all divided by +2, and I can handle the square root of -4 by representing it as 2i. So now 2 and 2i are both going to have to be divided by 2. So that's going to result in 1 plus or minus I. That's 2 complex zeros, and then -2 gave us our third 0, which matches the degree of our polynomial. So come back up here to where we said let a equal 1, and I'm now going to say c1 is equal to -2, c2 will be 1 plus I, and then c3 will be 1 minus I. And then I can substitute all those things in and get the statement g of x equals 1 times x minus -2 times x minus 1 plus I times x minus 1 minus I. And I'm very liberal with my parentheses here, and once I get them correctly set up, then I can think about how would I maybe better represent the individual factors. So for example, I would not keep that leading coefficient of 1. It can be implied, so I can just drop it. The first factor, I want it written as x plus 2. Second factor, I would want written as x minus 1 minus I. And then the third factor will be x minus 1 plus I. And that gives us the linear factorization, where we have one factor that is a real factor, and then we have two factors that are complex factors coming from the conjugate pair that was our zeros.